Bismillahirrahmanirrahim. Welcome to ceramic processing class. In this class, this is the first video. We will start with the chapter number 1, ceramic fabrication process. First of all, ceramics. Ceramics covers a wide range of materials. Broadly, it is divided into two parts, traditional ceramics and advanced ceramics. Traditional ceramics bear a close relationship to those materials that have been developed since the earliest civilization. They are pottery, structural clay products, and clay-based refractories. We may also include cements and concretes and glasses into traditional ceramics. The other one is the advanced ceramics. It was developed within the last 50 years. It includes functional ceramics that have electrical, magnetic, electronic, and optical applications, while the other one is the structural ceramics that are developed for certain structural applications at elevated temperatures. Now, this figure gives an important relationship in ceramic fabrication. First of all, the chemical composition. The chemical composition depends on the selection of starting materials. Purity of the materials are highly important in the selection of the composition. Structurally, if we talk about materials, they are either crystalline or amorphous. At atomic scale, the structure of material refers to the type of bondings and the crystal structure, whether the material is crystalline or amorphous. But at a larger scale, the structure of a material refers to the microstructure, which tells us about the nature, quantity, and the distribution of the structural elements or the phases present in the ceramics. Microstructure tells us also about the crystals, glasses, and even the porosity. The other thing which is very important is the properties. Properties of a ceramic play an important role in determining the application of fabricated ceramics. It is important to distinguish between the intrinsic properties of a material and the properties which are dependent on microstructure. As properties of a material is a combination of both these properties. First, intrinsic properties. The intrinsic properties are determined by the structure at the atomic scale. These properties are not subjected to change significantly by modification of microstructure. It includes melting point, elastic modulus, coefficient of thermal expansion, and whether the material is brittle, magnetic, ferroelectric, or semiconductor are all intrinsic properties. While the microstructure related properties includes its electrical properties, dielectric constant, its strength, these are all properties dependent on the microstructure. Now, ceramics, there are a number of methods, fabrication methods through which we can fabricate ceramics. Broadly, we divide the ceramic fabrication process on the basis of starting materials into three groups: the gaseous phases, the liquid phases, or the solid phase. Here the table shows some of the methods classified on the basis of the starting materials. Here you can see few have more than one starting material. First is the gaseous phase. By the gaseous phase, the method for fabrication is chemical vapor deposition. For gas-liquid phase is the directed metal oxidation method. For gas-solid starting material and liquid-solid starting material, both have a reaction bonding method. And for the liquid, we have sol gel process and the pyrolysis process. And lastly, if the starting material is a solid, we have melt casting method and the sintering of the powder. Now we will discuss one by one these phases. First of all, we will talk about the gas phase reaction or the gas phase reaction based fabrication methods. There are three types of gas phase reaction methods: chemical vapor deposition method, directed metal oxidation method, and the reaction bonding method. To briefly describe that, chemical vapor deposition method is the method in which the desired material is formed by chemical reaction between the gaseous species, while the directed metal oxidation method is a reaction between liquid and gases, while the third one, the reaction bonding, is the reaction between solids and liquids. First of all, the chemical vapor deposition method. Chemical vapor deposition method is a method in which chemical reaction between the gaseous species. Now, in the chemical vapor deposition method, reactive molecules in the gas phase are transported to a surface at which they chemically react and form a solid film. It is a well-established technique that can be used to deposit all classes of materials, including metals, ceramics, semiconductors, that can be used for a variety of applications. It is used for coating large areas and useful in mass production. Thin films, thick films, or even monolithic bodies can be fabricated by using chemical vapor deposition method. The required desired thickness of the film depends. If you prolong the deposition process, the thickness will increase and you can get the desired thickness of the material. Now, here we look at the process, how the chemical vapor deposition process actually happens. Here you see is the vessel. The vessel in which reaction takes place is the reaction chamber. The substrate to be coated is placed inside the reaction chamber. It could be any silicon or silicon dioxide vapor. First, the substrate is heated to desired temperature, which is about 200 to 200 centigrade. When the substrate reaches its desired temperature, then a continuous flow of reactant gases, mixed reactant gases, are introduced into reaction chamber. In this example, metal will be deposited on the substrate from metal chloride gas. Metal here is shown by blue atoms while chlorine is shown by green atoms. Metal is combined with chlorine to form a compound that can be maintained as gas. At the same time, we introduce a continuous flow of hydrogen gas, illustrated by red atoms. We adjust the process conditions such that the mixture does not react until it comes in contact with the solid surface of the substrate. When it comes in contact with the solid surface of the substrate, they are absorbed on the surface. They are held on the surface by weak localized attraction. The absorption allows the two gas molecules react together and create hydrogen chloride waste gas. This waste gas is evacuated from the reaction chamber, a vacuum created inside the reaction chamber. Meanwhile, metal initiates to be deposited on the substrate surface. With the passage of time, the whole surface is covered with the metal desired to be deposited. This is how metal is deposited on the substrate. Now, here are several factors that play a crucial role in the deposition process, chemical vapor deposition process. Now, let's see what are these factors. We call these factors the variables that influence the deposition process. These variables includes the flow rate of the reactant gases, the nature and the flow rate of an carrier gases, the pressure in the reaction vessel, the reaction chamber, and the temperature of the substrate. Substrate heating is required in chemical vapor deposition reactors because the films are produced preferably by endothermic reactions. The temperature of the substrate influences the deposition rate and is the main factor controlling the structure of the deposit. If we use higher the temperature, it yields a crystalline deposit, while if you use a lower temperature, it results in an amorphous material. And if you use a temperature which lies between two extremes, a polycrystalline deposit will be formed. Now, the other factor, very important, the pressure in the reaction vessel. It also influences the concentration of the reactant gases, the diffusion of reactants towards the substrate, and the diffusion of products away from the surface. The higher the diffusivity at lower pressure leads to the formation of film with better uniformity. Chemical vapor deposition reactors are mostly operated at 1 to 15 kilopascal pressure. Now the next factor, which is also important, that the precursor molecules, the reactant gases precursor molecules, these should be chosen to those that have good properties. Good properties means it includes that the thermal stability at its vaporization temperature and should have sufficient vapor pressure at a reasonable temperature, so it can be effectively used for the delivery, gas phase delivery, and for the growth. The molecules must be obtainable at high purity and must not undergo any side reaction which would lead to contamination or degradation of the film. Now, there are certain advantages and disadvantages of chemical vapor deposition method. First of all, advantage: low reaction temperature. The reaction temperature for fabrication of highly refractory ceramics using chemical vapor deposition method is very low as compared to the other methods we use for the fabrication. So, chemical vapor deposition method can be used to form highly refractory coatings, those having very high melting points, which are very difficult to fabricate by other processes, at a fairly low fabrication temperature using chemical vapor deposition method. Now comes the disadvantage. The main disadvantage of chemical vapor deposition method is it is very time consuming method. Material deposition rate is about 1 to 100 meter of thickness of the film per hour. So this makes this process very time consuming as well as expensive for the production of monolithic bodies. Another disadvantage is that this method is limited to thin films and coating, and it is not suitable for monolithic bodies because it develops a microstructural deformation, that is large columnar grains, which finally leads to a low intergranule strength. So it is limited for thin films and coatings, not for monolithic bodies. Now, we move on to the next gas phase reaction method, which is directed metal oxidation method. It involves the reaction between a gas and a liquid. And when we talk about the reaction between a gas and liquid, it is generally impracticable for the production of ceramic bodies, because the reaction product usually forms a solid protective coating which separates the reactants and effectively stops the reaction. But this novel method employing directed oxidation method, in this method a molten metal by a gas reaction by a gas has been developed especially for the production of porous and dense material, and as well as for the composites. The directed metal oxidation method is based on the reaction of molten metal with an oxidizing gas, and a liquid and a gas phase. Now we see the process here. Again, there is a refractory container. In this directed metal oxidation process, if we want to fabricate, consider a metal matrix composite. A molten metal, consider an aluminum alloy. Aluminum alloy in the molten form, here it is being present, is being oxidized by a gas, usually it is air, at a temperature which is mentioned over here, 900 to 1350 centigrade. And the aluminum alloy contains a few percentage of magnesium, which belongs to the group of fourth element, or you can use any element belonging to the fourth group. The oxide coating will be no longer a protective by the use of few percentage of that dopant of the fourth element. Instead, it contains small pores that forms a channel. A channel when molten metal is drawn up, through which the molten metal is drawn up to the top surface of the film, thereby continuing the oxidation process. As long as the molten metal and the oxidizing gas are available to sustain the process while the temperature is maintained, the reaction product continues to grow at a rate of a few centimeters per day until the desired thickness is obtained. The material produced in this way consists of two phases: the oxidation product, that is aluminum oxide, which is continuous and interconnected, and the unreacted metal alloys. The amount of unreacted metal is approximately 5 to 30 of the volume, depending on the starting material and the processing parameters, which is the temperature. And this directed metal oxidation process is also used for making the composite. By using this method, we can make a composite, a filler material, which can be shaped into any form that these particles, it can be shown over here. Preformed shape and size, they are used to reinforce in the aluminum oxide and the residual aluminum matrix, and they are the filler and the metal alloys are then heated to the growth temperature, while controlling the other conditions also, so that the oxidation process should continue and the metal surface such that the metal surface is reinforced by the filler materials. and finally we get a final product. If we consider silicon carbide fiber were reinforced in aluminum oxide and aluminum matrix, the optical micrograph would look like somewhat as mentioned over here, where here you can see the preformed shape of fibers that are embedded into the matrix of aluminum oxide. Now, the advantages. There are certain advantages of directed metal oxidation method. First, that the growth of matrix into the preforms, it involves little or no change in dimensions. Second, the problems associated with shrinkage during densification in other fabrication routes can be avoided. Third, large components can be produced readily with good control of the component dimensions. Now, here we move on to the third gas phase reaction method, is the reaction bonding. The term reaction bonding or reaction forming is commonly used to describe fabrication route where a porous solid preforms reacts with a gas or a liquid to produce the desired chemical compounds and bonding between the grains. Commonly, the process is accompanied by little or no shrinkage of the preform, so that very close dimensional tolerance can be achieved for the finished component. So this reaction bonding method, it involves both the gas liquid and the gas solid reactions. Now, if we see the figure over here, this figure shows that the reaction bonding process applied to fabricate reinforced metals. For example, if we consider magnesium doped aluminum alloy, first a preform of fibers, whiskers or particulates, we have to shape that material. As we are using aluminum alloys, so aluminum is made into a particular shape by using any sort of preforming methods: cold pressing, injection molding, slip casting, pressing in a die, etc. After the preform is produced, it is brought in contact with the molten alloy in a controlled atmosphere. For aluminum matrix composite, magnesium is used as a dopant, or you can say as an alloying element. Magnesium, it can be either added in the form of powder, or it is just added as an alloying element in a melted form to the melted matrix. The whole process is carried out in a flowing nitrogen gas atmosphere. In this case, the process temperature is about 800 centigrade. All the process is performed under controlled condition inside the chamber. By using the reaction bonding method, we can also produce silicon nitride, and production of silicon nitride is a solid gas reaction method. It means that the starting material is gas and solid. For the fabrication of silicon nitride, it is done by taking powder of silicon, shaped or preformed into particular desired shape, and then it is heated at atmospheric pressure in nitrogen gas environment at a temperature of 1250 to 1400 centigrade. So silicon nitride can be fabricated by using this reaction bonding method. Now the next is liquid precursor method. Earlier we studied the three gas phase reaction method. Now it is the liquid precursor method. Liquid precursor method, fabrication route in this, we use solution of metal compounds. The solution of metal compounds are converted into solid body. So we can say that the starting material is a liquid in this method. Liquid precursor method, most popular method is the sol gel process, which has attracted considerable interest since the mid 1970s, and it is used for the production of simple as well as certain complex oxides. Now what is sol gel process? Here you can see the flow chart illustrating the sol gel process. First of all, in sol gel process, a solution of metal compounds, or we can say a suspension of very fine particles in a liquid, which is usually referred as a sol, is converted into highly viscous mass, which we call it a gel. That is why this method is called sol gel process. The starting material normally consists of solution of metal alkalides in an appropriate alcohol in an appropriate amount with the alcohol. Here metal alkalides, you can see over here, M represents for the metal, whereas R is the R is the alkali group, and the OH here, the OH is the hydroxyl portion. In this solution, alcohol plus the water is added with the molecule. Its state is a diluted form, and under continuous stirring at temperature which is slightly above room temperature, normally it is 50 to 90 centigrade, and with suitable concentration of reactants and the pH of the solution, the process of hydrolysis and condensation occurs, which leads to the formation of polymeric gels. Polymeric gels, or it leads to the formation of two types of gels. Here it is important to distinguish between the two gels depending upon the sol or the solution which we are using. The gels produced are of two types. One is particulate gel. The particulate gel is in which gel material consists of colloidal particles that have been joined together by surface forces to form a network, while the other gel is the polymeric gel. Polymeric gel is a solution in which metal organic compounds form a network, or you can a chain of polymeric chain by undergoing the reactions of hydrolysis and condensation. After attaining these gels, the next process is the drying of the gel, and this process is certainly a time consuming process. As we attain a dry gel, it is sintered at certain temperature, and finally we get a dense product. Here we illustrate the particulate gel form and the polymeric gel, so the difference can be clearly visible. Now, the certain advantages and disadvantages of sol gel process. First, the disadvantage material production, the advantage, material production using the sol-gel process is highly pure. You can produce material with high purity, and the material produced have good chemical homogeneity. And another advantage is low densification temperature. While there are certain disadvantage of sol-gel process, as discussed earlier, that the drying process is very time consuming, and it causes certain difficulties, the cracking, wrapping, and considerable shrinkage of the material. And another disadvantage is that the starting material, the metal alkalides we use in sol-gel process, are fairly very expensive one. Now comes the fabrication from the powder. Fabrication from the powder is that we are referring that the starting material in the fabrication process will be in a solid form. There are two types of fabrication method which use solid as a starting material. First, melt casting method. Generally it is melting followed by the casting into a specific shape. This process involves. Second is the firing of compacted powder. So these two fabrication processes are originated from the earliest civilization, and still they are used. Melt casting method, as mentioned earlier, is the method in which material, the powdered form, is melted by using high temperature. Then the molten material is casted into specific shape, and it simply refers to the melt casting technique, and it is usually very popularly used for the production of glasses. But melt casting techniques have certain disadvantage. First, the grain growth is uncontrolled, and this uncontrolled grain growth causes severe problems, and this leads to the production of ceramics, those having undesirable properties like strength, low strength. Another problem with this melt casting technique is the fabrication of certain ceramics. Those have very high melting temperatures, like zirconium oxide, which has a melting temperature of 2600 centigrade. By using this method, these higher temperature ceramics decompose prior to melting, or it is very difficult to obtain melt of these high melting temperature materials. So this method, melt casting method, is limited for the fabrication of the glasses. But there are certain advantages of melt casting method. The first advantage is that melt casting method is very useful in the production of glass ceramic roots. The glass ceramic roots has the advantage of economical fabrication by conventional glass manufacturing methods. Gas ceramics are fabricated in the way that the raw materials are first melted and then formed into shape, which is in the glassy form. We are still in the glassy state, and then they are heat treated. They are heat treated mainly by using two-step method, nucleation and crystal growth. A low temperature hold to introduce nucleation of crystals, which is followed by one or more higher temperature that will promote the growth of crystals throughout the glass. Glass ceramics are materials that by volume has 50% of the crystalline phase, or you can say it has 90% of the crystalline phase. So melt casting technique is important for the production of glass ceramics, those materials that which have high strength, chemical durability, and it have electrical resistance, and it has very low. So certainly it is useful for the production of materials that can be applicable to certain broad range of applications it can be used. The second method is firing of compacted powder. It is also a simplest form of the matter, in which it involves the consolidation of a mass of a fine particle to form a porous shaped powder, which is then fired to produce a dense product. Although in principle this route can be used for the production of both the glasses and polycrystalline ceramics, but practically it is hardly ever used for the production of glasses, because economically a cheaper method of melt casting is present, which can be utilized for the production of the glasses. However, it is widely used for the production of polycrystalline ceramics. Now here this figure illustrates the various processing steps involved in firing of consolidation of the compacted powder process. Powder which is mixed, consolidated, debinded, shaped into the form and fired, and finally we get a dense product. Now if we summarize the whole production method, the whole fabrication process, we see that in the flowchart we also have seen that the fabrication of ceramics from the powders it involves number of steps, but majorly we can divide the processing steps into two parts: processes that occur before firing or sintering of the green body, and those that occur after the sintering. Now each step, production step or the processing step, has undesirable microstructural flaws. It causes undesirable microstructural flaws that will certainly limit the properties and the reliability of the material. So it is important to study each and every step. First is the powder synthesis and powder characterization. Second is the powder consolidation. The third one is the firing process, and the fourth one is ceramic microstructure. Now all these methods here, first of all, for the powder synthesis and powder characterization, it is very important to select materials that are free from contamination, because contamination can alter the microstructure and it will affect the properties of the fabricated material. So extreme care should be taken during the selection of the powder. While the powder consolidation For the powder consolidation, we usually refers to the powder consolidation. We refers that it is during the fabrication process, or when the green body is forming. Then the forming method, during the forming methods, uh, the powders can consolidate. It will alter the particle size and will create agglomeration. So the particle size will not remain homogeneous, which will also alter the microstructure. The third one, which is the firing process. The firing process is very important. In order to have the desired microstructure, the selection of the temperature at which you can attain the desired phase or the desired microstructure is very important, because there are certain range of temperature at which a certain phase can exist. If the temperature is less than that phase, the phase will not develop, and if the temperature is greater than that range, the developed phase will decompose. So the temperature should be controlled in order to have the desired end product with desired properties. The major problem in the firing process is that if the consolidation of the powder, if the particles are agglomerated in that process, then during firing or the sintering process, it will cause coursing of the product, and it will lead to a heterogeneous microstructure. So it is important that the particles should be homogeneous, the size of the particles should be homogeneous before the sintering process. Lastly, the microstructure. By examining the microstructure, we can identify the flaws which has deteriorated the properties of the end product which was desirable. At this stage, we can see what was the flaws left. Either it was left due to during the first process, in which contamination caused the microstructural flaws, or the consolidation process, or during the firing process. And by studying the microstructure, we can eliminate these flaws. So this was all about ceramic fabrication process.